Okay, so welcome back. This is part 2 in our series where we're helping you to understand how your laptop computer, especially your motherboard, works and what are the different circuits here. And the goal is to help you to understand so that if, for example, you want to work on your laptop motherboard, it'll give you some insight into what's actually on the motherboard and how it works, so that you can really understand what you're doing and you can figure out how to test it to check if it's good or if there's any problems. Now, unfortunately, on the internet, a lot of people like to just sit back and watch a video and somebody will tell you measure this, measure this, measure this, but you don't really understand what's going on, and often they don't even understand what's going on. But you watch that and you think, oh well, I know that measure this, this, and this, therefore I'm an expert. Well, unfortunately, that's not true. You really need to understand what's going on the motherboard and why it's doing that. And on this channel, we are all about learning about these things. And in fact, what we're going to do in this series is not only learn about the different circuits, but we're also going to simulate them using a free piece of software called LT Spice, where you can basically drag and drop components, wire them up, and simulate how they work in the real world, so you can get a much better understanding of what signals you should see, what voltages, what powers, what currents, that kind of thing. So the goal here, like most of the videos on this channel, are to help you to actually understand so that you can figure this stuff out for yourself. Now, in part 1, we focused on arguably the most important part. If you're going to be working on a motherboard, the most important part is the input voltage source that's coming into your motherboard that will ultimately power all of the components on the motherboard. So we showed how the power coming to the motherboard ultimately comes from either a wall adapter like you see here or a battery. And the wall adapter is obviously plugged into the wall outlet, and the wall outlet is feeding it something like you see here, a sine wave in the US, 120 volts AC RMS. And what this adapter does is it converts that AC 120 volts to a DC around 19 volts and feeds all of the components. However, the components don't generally use the 19 volts coming in. What we talked about last time is there is some circuitry in here that will convert that 19 volts into a bunch of different other DC voltage levels that are required by your computer. And here we've got some examples of the different DC voltage levels required by the components. The CPU 1 to 2 volts, GPU 1/2 to 2 volts, the RAM, and so on. And there's a lot of circuitry on this motherboard whose sole purpose is to convert the 19 volts to these different voltage levels. And once you understand the simple circuitry that does that, a lot of what appears on this motherboard turn out to be fairly simple concepts. So what we're going to focus on in this video is looking at that simple circuit with only a few components that will take the 19 volts and convert it to one of these other voltage levels required by the components on the motherboard. Now, in order to get a better understanding of what those actual voltage levels are, you can go to a good computer. Of course, you can't do it with a dead laptop, but you can go to a good computer and you can run a piece of software, a free piece of software, such as HW Info. And here is a window from HW Info that shows for the CPU. Down here we've got the V-core, what the different voltages are, and you can get an idea about what these actual voltages are on your running computer, just to give you some insight into what those levels are. You can also look at CPU ID HW Monitor, another free piece of software. And you can see here the voltages, 3.3 volts is actually 3.296. And here's the min and max. CPU V-core, the dynamic RAM is 1.2 volts. 12 volts is 12.28 and so on. And then we can see our CPU VDD is 0.89. And we can go down to our GPU, in my case it's an RTX 2070 Super. The voltages on the GPU are 0.65 volts. So it's really good to just run these and get a feel for what voltages you might expect on your motherboard based on what the actual good voltages are. So now let's start taking a look at the basic concepts behind the simple circuit that's used to convert from 19 volts or 12 volts from the battery down to these lower voltages that are distributed around the motherboard. So here we're going to start with a simple circuit, and you can see I've got 19 volts presumably coming from the AC wall adapter, and in red I've got two switches. One of them is closed up here and one is open. And the center tap between these two switches is our output voltage. So let's think about what is the output voltage as shown here where the switch is closed and this switch is open. Well, 19 volts is connected from here to the output and this is open. Therefore, the potential between this output and ground is going to be 19 volts. So in this position of the switches, we're going to expect to see 19 volts. So as soon as I close this switch, I'm going to go from 0 volts up to 19 as long as this switch is open. What if I swap the switch positions? In other words, I open this and close this. Well, suddenly this output is going to be connected directly to ground or 0 volts, and this is going to be open, so you will expect to see the output voltage go from 19 back down to 0. So I can do it again, and you can start to see that if I can control these switches electronically, I can generate a square wave waveform that looks like this. Well, so what? What are you going to do with this? Well, you can imagine, depending on how I set the timing to these switches, I can keep this switch closed for a very short amount of time, and I would get a waveform that looks like this. So by modifying the timing of these switches, I can get different pulse widths of this waveform. Now, this may be familiar if you've ever looked at electronics before. This is what's called pulse width modulation, where the width of these pulses is varied or modulated by the timing of these switches. So if I keep this switch closed longer, I get a waveform like this. If I keep it closed shorter, I get a waveform like this. Well, so what? How is that going to help us? Well, the difference between these two waveforms can be looked at as they have different average values. So for example, if I keep the top switch closed for the same amount of time that it's open, I have a pulse width that is 19 volts and 0 volts for the same amount of time. That's called a 50% duty cycle. And what that means is the average value of that waveform, since it's 50% of the time at 19 and 50% of the time at 0, the average value is half of 19 or 9.5 volts. So if I keep the switch closed shorter amount of time, the pulse width gets much smaller, and therefore the average value of that 19 volts might only be 3.8 volts. So you can start to see, as I do pulse width modulation, I vary the timing of those switches. I can go from, if the switch is always closed, the top switch is always closed, it will always be 19. If it's always open, it will be 0. And timing in between that can allow me to get a different average value of that waveform. So the concept is, if there's some way I can figure out the average value of this waveform and convert that to a DC voltage, I can now, only by changing the timing of those switches, I can get a voltage anywhere between 19 volts and 0 volts just by changing the timing of those switches. That is an extremely important concept, and it's used in every single one of the what's called DC to DC converters that take the 19 volts and converts it into the 1 volt or 2 volts or 5 volts or 3 volts or whatever is needed by the components on your motherboard. So now let's take a look at how we can figure out what the average value of those waveforms is and convert that to an equivalent DC. Well, the first thing we're going to do is we're going to replace those switches by what's called a MOSFET, a metal oxide semiconductor field effect transistor, which is basically exactly what we want. It is a switch that is remotely controlled by some electronic signal. And by controlling that electronic signal, you can vary the pulse width. Again, that's called pulse width modulation. So the MOSFETs, as we vary the timing of those MOSFETs, we're going to be getting a voltage at this point here that is a PWM signal. However, we have to feed it through some circuit that will convert that to an average value. In our case, we might want, say, 3.3 volts. So what is this circuit going to look like that's going to convert this weird-looking pulse into a flat DC of equal to the average value of that waveform? Well, what we're going to apply is a very simple filter called an LC filter, which basically takes these high-frequency, sharp pulses and converts it into a flat DC. And we're going to use an inductor in series with that and a capacitor in parallel. That's where you get the LC from. The L is an inductor and the C is a capacitor. Now, the inductor serves to slow down the current going through this circuit. So, for example, if I had nothing here and I was just feeding a resistor, I would get a current through this circuit that would look just like this voltage. What the inductor will do, it will change the current to slow down depending on the size of the inductor. So instead of a straight up voltage, it will rise slower. When the voltage goes away, it will decrease slower. The capacitor does the same thing for the voltage at this point. So the combination of the inductor and the capacitor serves to flatten out these pulses into a flat voltage. So if we look at the input voltage, the output voltage without this capacitor will look something like this, where this fast rise becomes more of a slow rise and a slow decay. And then if we add the capacitor, it will change the voltage to be just a very almost flat with what's called ripple. So depending on the size of the inductor and the capacitor, we can convert this pulsed wave into a nice flat DC that is equal to the average value of this waveform. So you should expect in your motherboard to see this circuit reproduced over and over again. 2 MOSFETs, an inductor, and a capacitor. And depending on the timing of these MOSFETs opening and closing, you can vary that output voltage. Now, one other thing I want to mention. Here we have a 19 volts feeding this circuit that converts it through PWM to a lower voltage. Keep in mind, I can change this to say 40 volts if I want and still get 3.3 volts. Because all this controller has to do that's controlling these MOSFETs, it has to just change the duty cycle to give a different percentage of that 40 volts to get the 3 volts. So that's the nice thing about this. You can put just about any voltage you want here, and all you have to do is change the timing of the switching of the MOSFETs to get a smaller duty cycle, and that will still give you the 3.3 volts. So keep that in mind. That's a very important concept. So this is the circuit you're going to see virtually everywhere on your motherboard. Again, there's going to be variations, but this is the general concept. And we're going to be feeding a signal into these gates of the MOSFET, and they are going to be switching on and off and feeding that pulse width modulated waveform to this circuit. Now, to control these, we're going to have some circuit that will feed these control signals to switch these MOSFETs on and off. Now, I did a video on MOSFETs and ATX power supplies. This is very similar to circuits used in a computer ATX power supply. I encourage you to take a look at that. But basically, we're going to have some very low voltage, low current signals who turn this on and off. And with a MOSFET, you can use low voltage, low current signals, and it will switch high voltage, high current signals into this inductor and capacitor. So we're going to expect to have 2 MOSFETs, an inductor, a capacitor, and some sort of integrated circuit that provides control to these MOSFETs. And they're going to look like this. You can expect to see an inductor that looks like this, capacitors that look like this, or you may have a larger capacitor we'll talk about later, and then MOSFETs that generally look like this. So you should expect to see this set of components or variations of this repeated over and over on your motherboard, where we can convert to the 1 volt or 3 volts or 5 volts or whatever is used by the particular component on the motherboard. Now, this MOSFET has a gate, a drain, and a source. And as we said, high currents and high voltages are traveling through the drain and the source, but low voltage, low current signals go to the gate to switch it on and off. So you will see generally like an 8-pin MOSFET where the drain has 4 pins tied together to allow it to carry more current. The source has 3 pins tied together to allow it to carry current, but the gate is only 1 pin because it's a low voltage, low current signal. So let's look at a photo of a motherboard and see if we can now identify some components here that look like what we just talked about. Well, you can see here we've got these big 2R2, 1R0, 1R5, 1R0. Those are the coils, the inductors we just talked about. So we can start to see, hey, maybe we've got 1, 2, 3, 4, 5 sections that are converting our 19 volts into lower voltages. So what else can we determine? Well, we said we're going to have probably 2 MOSFETs right near them to do the switching. Well, if you look up here, we've got our inductor and we've got a MOSFET and a MOSFET. We've got 4 pins on the top, 4 pins on the bottom. So this is very likely a inductor with MOSFETs. We've got some capacitors here. What about this down here? We've got an inductor, we've got 2 MOSFETs, we've got some capacitors, so here's another one. What about this here? We've got an inductor, we've got this 4 pins and 4 pins. We've got some capacitors. Maybe this is a MOSFET. We're going to talk about that in a bit. So you can start to see we have already decided there are some sections here where we are converting our 19 volts or 12 volts down to the required voltage. Now we also have these pins here with each of them has, like 20 pins, 5 pins, 5 pins, 5 pins, 5 pins. Maybe these are the controller pins that are controlling the switching of the MOSFETs for these coils and capacitors. So you can start to see maybe we've got some sections here that we already understand how they work. Now, one thing you need to be aware of with electronic circuits is there are always variations. Manufacturers love to modify things, and maybe where one time you need 2 components like our 2 MOSFETs, they will go through and say, hey, I've got a new version that puts 2 MOSFETs on 1 chip. So I have 1 integrated circuit that's got 2 MOSFETs on it. That's why when you go down here, you see here's my coil, and here it looks like 1 MOSFET with 4 pins and 4 pins. In fact, that is 2 MOSFETs in 1 chip. Now, if you look at the data sheet for that particular MOSFET, you can see, well, how do they get, with 4 pins and 4 pins, how do they get the correct pin outs? So you can see we come in with our 19 volts here on this D1, our first MOSFET or the top MOSFET, and then it goes to our output, and here's the bottom or second MOSFET. And this is going to be connected to ground. So what they do is they actually have, instead of just 4 pins on the top and 4 pins on the bottom, they've actually got another section that is connected underneath for the output. Just keep in mind, it's these kinds of things you're going to see often in your electronic circuits where you think you know what it is, but in fact you need to look at the data sheet to see what's going on. So now that we have a fairly basic idea of what's going on with these sections in the motherboard where you are converting from 19 volts or 12 volts to whatever lower voltage, 1 volt, 3 volt, 5 volt, whatever, we can start to think about going into the motherboard when it's running and powered on. We should be able to measure some voltages and know what to expect. So for example, we said where we've got 2 MOSFETs, we've got an inductor and a capacitor, we could probably go to these inductors, and on one side we should measure a voltage to ground that is a PWM signal, as you see here. On the other side, it should be a flat DC of the value that it's converting to, like 3 volts or 5 volts or whatever. So we should have a pretty good idea of what to expect. Now, keep in mind, you have to be very careful. If you're going to use your oscilloscope in an electronic circuit, do not connect your ground lead of your oscilloscope probe to anything other than ground, because, for example, you can short out a MOSFET, you can get a short circuit by connecting it to ground, so be very, very careful. So at this point, we should be able to get a good feel for what's going on, and then we can, for example, take our multimeter, and for your homework, you can figure out, well, if I hook my multimeter out to this side, I should get a DC of 3.3 volts. What is the multimeter going to show if I hook it up to this PWM signal? Is it going to give me the average value? Is it going to give me the same thing? So that's an interesting thing to consider. But at least at this point, we should be able to have a pretty good idea of what's going on. You know, what signals are coming into the gate of the MOSFET, what is the output, and you know, what should we expect? Now, in the next part of this series, we are going to simulate something like the circuit you see here with a controller, some MOSFETs, inductor, and capacitor. And we're going to go in and actually probe on our computer in the simulation the currents, the voltages, the powers, so we can get a good feel for what to expect. And then maybe when we go in to measure actual bench voltages, we know exactly what to expect and we have a better understanding of what's going on. So that's it for this one. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.